My name is Shengyao Zhuang. I'm a PhD student from IE Lab at the University of Queensland. So this video is about our SIGIR2021 paper, TILDE Turn-Independent Likelihood Model for Passage Re-ranking. This is joint work with my supervisor Guido Zukan. So the problem that our paper deals with is the passage or document ranking problem. The classic document ranking models such as BM25, TF-IDF, or Unigram language model are based on exact term matching method. This group of methods build inverted index for documents in the collection, and each document can be considered as kind of sparse vector, where the dimension is the size of a vocabulary and the elements are the term frequency. Since all documents are represented by sparse vector, there are many tricks that can make the ranking to be very fast. However, it is well known that this exact term matching methods cannot provide semantic matching signals, and they are suffering from keyword mismatch problem. So to solve this problem, many works are focusing on designing neural rankers, especially with the development of pre-trained deep language models. The community moved the attention to design BERT-based rankers. Unlike exact term matching models, BERT-based rankers encode documents into dense representations in the embedding space. As the result, these BERT-based neural rankers can provide strong semantic matching signals between queries and documents, thus showing better effectiveness than exact term matching method. However, one main problem of BERT-based rankers is that they are very inefficient. This is because BERT model is a deep neural network with millions of parameters, thus it is very expensive to inference. So there are two main groups of BERT-based rankers. The first group is called cross-encoder, where query and query tokens are paired with document tokens and input to the BERT model as a whole. The output of the BERT model is the dense representation of query document pair, which will be used to estimate a matching score. This architecture allows the query tokens to interact with document tokens. It has been shown to be the most effective ranking model, but this architecture is also the most inefficient, as it needs multiple inference steps to compute matching scores for all the query and document pairs. The second group is called bi-encoder, or sometimes also called dual encoder. This architecture uses semi-BERT model or two different BERT models to separately encode queries and documents into dense representation. The matching score is usually estimated by similarity score between the query vector and the document vector. As there is no interaction between query and document during the encoding step, the document representation can be pre-computed and stored in the index. At the query time, there is only one BERT inference is needed to get query representation. Hence, bi-encoder is much more efficient than cross-encoder. The drawback of this architecture is that query can only interact with document at the final stage, thus it is usually less effective than cross-encoder. Although the bi-encoder massively improved the efficiency for BERT rankers, there is still a step of deep neural network inference, which means you need to have a powerful GPU to deploy these rankers in production. This means it is hard to use these powerful rankers in small GPU-free devices such as mobile phone. So this problem motivates us to think about the question that can we actually achieve zero GPU inference for BERT-based rankers at a query time? Based on this motivation, we designed our model, TILDE. So our model is still a bi-encoder architecture, so we still use BERT to pre-compute document representations. However, for a query encoder, we simply use the BERT tokenizer to tokenize queries and encode query into a sparse vector. So this is kind of similar to exact term matching method, where the query vectors has the length of vocabulary size, and each element in the vector is a token appearance in the query. On the other hand, in order to do the similarity search, we add a linear layer on top of document representation to map it to the same dimension as query sparse representation. An interesting thing to know is that in our architecture, the semantic matching is still hold because even if the query uses a keyword that does not appear in the document, but because the document is dense vector encoded by BERT, it still can have high value for that keyword in the dense representation. So since now the query encoder is just a tokenizer, which is a small lookup table, we can encode query very fast without GPU. Another key difference between our model and the other bytecode model is the loss function. Instead of margin loss or contrastive loss that are used for a classic byteencoder, we actually train our model with traditional query likelihood loss function used for information retrieval. So more specifically, we assume query tokens are independent, which is a common assumption used in query likelihood models. And we propose bidirectional query document likelihood loss function for training our model. So this BiQDL has two directions. The first direction is the traditional query likelihood loss. So for each relevant query document pair in the training set, the model takes the document text as the input, and for each token in the vocabulary, or in other words, for each element in the query sparse vector, if the token is in the query, then the loss will increase the probability of generating this token. Otherwise, it decreases the probability. The second direction is the document likelihood loss, where we simply swap the query input and the document input to the model. So in this case, query will be encoded into dense representation by BERT, but the document will be encoded into sparse representation by the tokenizer. And the BiQDL is just the sum of the both direction and divided by 2. So after training with this loss function, TILDE can actually estimate query likelihood given a document text, or also it can estimate document likelihood given the query text. So this means TILDE can have different re-ranking settings. It can rank documents by query only based on query likelihood score, or it can rank documents according to document likelihood score. So in this setting, all the scores need to be normalized by dividing the document length, since longer documents tend to have lower likelihood score. Also, GPU is required in this case because now the BERT input is the query, and we cannot pre-compute queries representation because we won't know what will be the user next query. In addition, you also can estimate the relevance score by interpolating the two scores, and the ratio can be controlled by a hyperparameter alpha. For experimental details, we use MS-MARCO passage dataset to train our model TILDE. This is one of the most commonly used dataset for training BERT-based rankers. For the BERT encoder using our model, we use a BERT-based uncased model. We use all relevant query passage pairs in the dataset to train our model, and we train it with 10 epochs with batch size of 128. So we also did vocabulary cleaning for the BERT tokenizer by removing stop words and symbols in the lookup table, resulting in the vocabulary size reduced from more than 30,000 to about 28,000. We found this can help to improve the model effectiveness. We evaluate our model on MS-MARCO dev set and track deep learning 2019 and 2020. We use MMR10 for MS-MARCO and NDC-JET10 and MAP for track deep learning. So these evaluation metrics are the official metrics. For results on MS-MARCO dataset, we use BERT-based rankers to re-rank top 1,000 documents retrieved by BM25. We also report the query latency for each method. So for byteencoder method, the query latency is estimated by a query inference time plus re-ranking time. So first, for BM25 baseline, it can achieve 0.187 on MMR at 10 score, and it has only 130 millisecond query latency. Then we report a cross-encoder BERT-based rankers called BERT large. So it can achieve very high MMR score, but it also has a very high query latency even on a GPU machine. Then we tested a bi-encoder model called EPIC. As the result we show here, it is less effective than cross-encoder model, but it is much more efficient. In fact, we tested query latency for EPIC on a pure CPU environment, so the query inference time is still considerable. Then we report our TILDE model with query likelihood ranking setting. We surprisingly find our model can achieve almost the same effectiveness as EPIC, but with much more efficient query inference time. So remember in this setting, the query encoder is just a lookup table, hence it can achieve less than 1 millisecond query inference time, even under the pure CPU environment. We then tested our model with the interpolation of query and document likelihood ranking setting. So in this case, we do need to inference the query and the document in both directions. Hence, the BERT inference step for the query. So there is another BERT inference step to encode the query representation. So the query latency becomes the same level as EPIC. But we did report a better MR score than EPIC and TILDE, and also TILDE with only query likelihood. So suggesting that adding document likelihood signal to our model can further improve the effectiveness. Although we did not find statistical significance among these three bi-encoders. The results on deep learning collection are more or less the same. Again, we did not find statistical significance between TILDE and EPIC. So in this slide, I investigate the impact of document likelihood signal on our model effectiveness. As you remember, the TILDE QDL is the interpolation between query likelihood and document likelihood controlled by a parameter alpha. So in these two plots, I show the changes of NDCG and map scores with the changes of alpha. When alpha equals to 0, means the documents are ranked only based on the document likelihood. As the plot show here, that the performance is very bad in this case, meaning document cannot be ranked solely with document likelihood. However, the best performance is achieved when alpha equals 0.4 to 0.5, which further confirms that document likelihood is beneficial to our model. So when alpha equals 1, which is the pure query likelihood ranking setting, the performance only slightly dropped. Provided that in this setting, TILDE has the minimum query latency, so we believe it is better and safe to just use alpha equals 1 if you don't have a GPU device. To conclude our work, we propose TILDE, a novel bi-encoder BERT-based ranker. We replaced the expensive BERT query encoder with a simple, efficient tokenizer-based encoder. TILDE does not need a GPU at query time, thus it can be used on consumer embedded devices such as mobile phones. The important takeaway message from our paper, so TILDE actually shows that query encoder in bi-encoder architecture can be heavily simplified without hurting too much effectiveness. This is actually intuitive, as queries are usually much shorter than documents, and sometimes they're just a single keyword. Hence, we actually don't need the full size of BERT in order to get a good query representation. But a simplified query encoder can give massive efficiency gain. So we believe how to design a simple but efficient effective query encoder for bi-encoder architecture could be an interesting research direction. More information about our paper, please visit our website. Thank you for listening.